Today we explore one of the most fascinating paradoxes in modern physics: how materials can be perfect insulators inside, yet perfect conductors on their surface. Imagine a material where electrons flow freely on the surface like a superhighway, but the interior is completely blocked like an impenetrable wall. This is the topological insulator. Let's start by understanding why this seems impossible at first glance. In ordinary materials, if something conducts electricity, it conducts everywhere. If it's an insulator, it insulates everywhere. In a normal conductor, electrons can move freely throughout the entire volume of the material. In a normal insulator, electrons are trapped and cannot move freely anywhere in the material. But topological insulators completely violate this assumption, creating a sharp boundary between conducting and insulating regions. To understand this paradox, we need to explore the concept of electronic band gaps. The band gap is the energy difference between the conduction band, where electrons can move freely, and the valence band, where they're bound. Here's a band diagram showing the energy gap between the valence band below and the conduction band above. This gap determines whether a material conducts or insulates. For reference, silicon has a band gap of about 1.1 electron volts, while diamond has a much larger gap of 5.5 electron volts. 1 electron volt equals 1.6 times 10 to the minus 19 joules, which is the energy scale of atomic interactions. Here's the key question. If the bulk material has a band gap that prevents conduction, how can electrons suddenly conduct on the surface? The answer lies in a branch of mathematics called topology, which studies properties that don't change under continuous deformations. In topology, a coffee mug and a donut are considered the same, because you can continuously deform one into the other without tearing. They both have one hole. A topological invariant is a number that characterizes the shape and doesn't change no matter how you stretch or bend the object, as long as you don't tear it. For topological insulators, the Chern number nu is calculated by integrating a quantity called the Berry curvature over the Brillouin zone. The Chern number must be an integer, like 0, 1, or 2. It cannot be 0.5 or 1.7. This quantization is crucial. Now we reach the heart of the paradox, the bulk boundary correspondence principle. The bulk boundary correspondence states that if the bulk has a non-trivial topological number, there must be conducting states on the boundary. It's a mathematical necessity. This isn't just an experimental observation. It's a mathematical theorem. Non-trivial topology in the bulk guarantees surface states. Mathematically, if the bulk Chern number is not 0, then surface states must exist. There's no way around it. You might ask, why can't we just remove these surface states? Can't we modify the surface somehow? The answer is no. These surface states are topologically protected. Any small perturbation cannot remove them, because that would require changing the bulk topology. Let's understand how this topological protection actually works at a microscopic level. Imagine trying to change the topological number from 1 to 0. You'd need to pass through intermediate states. But here's the catch. To change the topological number, you must close the band gap somewhere in the material. The gap must go to 0. But closing a gap of order 0.3 electron volts requires energy much larger than thermal energy, which at room temperature is only 0.025 electron volts. At room temperature of 300 Kelvin, thermal energy is about 0.025 electron volts. Therefore, surface states are protected by an energy barrier equal to the bulk band gap, making them incredibly robust. There's another beautiful feature of topological surface states: spin momentum locking. In topological surface states, the electron's spin direction is locked perpendicular to its momentum. If it moves right, its spin points up. If it moves left, its spin points down. Mathematically, the spin vector s is perpendicular to the momentum vector p. This relationship is rigidly enforced by topology. This spin-momentum locking has a profound consequence. It prevents electrons from scattering backward when they hit ordinary impurities. When an electron encounters an impurity, it cannot simply turn around and go backward, because that would require flipping its spin, which costs too much energy. Let's look at some real topological insulators that have been discovered and studied. Bismuth selenide, with chemical formula Bi2Se3, is the most famous three-dimensional topological insulator. Bismuth selenide has a bulk band gap of about 0.3 electron volts, large enough to persist even at room temperature. The crystal structure consists of layers of bismuth and selenium atoms arranged in a hexagonal pattern. The surface of bismuth selenide has a conductivity of about 0.01 Siemens, which is quite good for such thin surface layers. Other important topological insulators include antimony telluride and mercury telluride, each with their own unique properties. Let's quantify the energy scales that make topological protection work in practice. At room temperature of 300 Kelvin, thermal energy is only 0.025 electron volts. The topological band gap is about 0.3 electron volts, which is 12 times larger than thermal energy. This ratio of 12 means the surface states are extremely stable against thermal fluctuations at room temperature. For comparison, breaking a typical chemical bond requires 1 to 5 electron volts, which is even more energy. This bar chart shows the relative energy scales. Thermal energy is tiny, the topological gap is moderate, and chemical bonds are the strongest. Now let's address why the surface conduction is essentially perfect, with no resistance. In normal conductors, electrons scatter off impurities and defects, creating electrical resistance that dissipates energy as heat. Resistance equals resistivity times length divided by area. The resistivity depends on how much electrons scatter. In normal materials, electrons zigzag through the material, constantly scattering off impurities, which creates resistance. But in topological surface states, backscattering is forbidden by the spin-momentum locking we discussed earlier. The surface resistivity is extremely low, about 10 to the minus 6 to 10 to the minus 8 ohm meters, approaching the quantum limit. Topological insulators are closely related to another famous phenomenon, the quantum Hall effect. In the quantum Hall effect, a magnetic field causes electrons to flow in one direction along the edge, while the bulk remains insulating. The Hall conductivity is quantized in units of E squared over h, where E is electron charge and h is Planck's constant. This quantization is incredibly precise, accurate to better than 1 part in 10 billion, making it useful for resistance standards. Topological insulators achieve a similar effect without any external magnetic field, using spin-orbit coupling instead. What can we do with these remarkable materials? Let's explore potential applications. Topological insulators are promising for spintronics, where we use electron spin rather than charge to carry information. A topological insulator device could process spin information with extremely low power dissipation. Even more exciting is quantum computing, where topological properties could create qubits that are naturally protected from errors. The dissipationless surface currents could enable ultra-low power electronic devices that barely heat up. Power dissipation equals current squared times resistance. As resistance approaches zero, so does power loss. How do scientists experimentally verify that a material is a topological insulator? The primary technique is angle-resolved photoemission spectroscopy, or ARPES, which maps the electronic band structure. In ARPES, photons hit the sample and knock out electrons, whose energy and angle revealed the band structure. Scientists look for a characteristic Dirac cone in the surface band structure, where energy varies linearly with momentum. The Dirac cone has a linear dispersion relation. Energy equals h bar times the Fermi velocity times the magnitude of momentum k. The Fermi velocity in these materials is about 1 million meters per second, which is about 1% of the speed of light. A crucial ingredient for topological insulators is strong spin-orbit coupling. Spin-orbit coupling is an interaction between an electron's spin and its orbital motion through the material. The spin-orbit Hamiltonian involves a cross product of momentum p and spin s with strength parameter alpha. As the electron moves with momentum p, its spin s experiences an effective magnetic field that depends on the momentum direction. Heavy elements like bismuth and mercury have very strong spin-orbit coupling because it scales with atomic number to the 4th power. The spin-orbit coupling strength alpha scales as z to the 4th power, where z is atomic number. How do temperature and thermal fluctuations affect topological protection? Because the bulk gap is large compared to thermal energy, surface states persist robustly up to very high temperatures. This graph shows how conductivity remains high, even as temperature increases, only decreasing slightly due to phonon scattering. Topological properties remain robust up to temperatures around 350 Kelvin, which is above room temperature. However, at high temperatures, bulk conduction can increase and obscure the surface states, making them harder to observe. Let's return to our original question. Why does this seem paradoxical? Our classical intuition says that properties at a boundary should be some average of the properties on either side. If you have insulator A and insulator B meeting at a boundary, you'd expect the boundary to also be insulating. But topology creates entirely new physics at the boundary that doesn't exist in either bulk material. Incredibly, insulator plus vacuum equals conductor at the interface. This violates our everyday intuition. The resolution is that topology is a non-local property. It depends on the global structure of the band, not just local values. Let's bring together all the pieces to resolve the topological protection paradox. First, the bulk material has a topological invariant, the churn number, which must be an integer. This invariant cannot change without closing the band gap, which requires enormous energy. At a boundary with vacuum, or a trivial insulator, the topological invariant must change from non-zero to zero. The only way this change can happen is through gapless conducting states at the boundary ITS. This diagram summarizes the resolution. The bulk with nu equals 1 must connect to vacuum with nu equals 0 through conducting surface states. Perfect insulation in the bulk and perfect conduction on the surface coexist not by accident, but by mathematical necessity. Topology guarantees that both must exist simultaneously. You cannot have one without the other. The paradox is resolved. Both the bulk insulation and surface conduction are inevitable consequences of the same topological structure. Topological insulators represent a beautiful unification of mathematics and physics. This is a rare case where pure mathematics, specifically topology, predicted new physical phenomena before they were observed. Robustness comes from global topology, which prevents the system from becoming a trivial insulator.